Hello everyone. Every now and then I'll add some videos as additional study sources. These videos highlight new concepts or give you some feedback or answer some frequently asked questions raised in tutorials or in lectures. The first of these videos I'll define the concept of population, sample, and random variables and their distributions. Statistics is the science of collecting, organizing, summarizing, visualizing, and analyzing data to answer interesting questions or important questions. In the first year statistics, you spend a lot of time on organizing data and summarizing data and visualizing it using things like histograms or time plots. When it came to analyzing data and learning from the data, which was in the second half of the first year, you started thinking about the bigger picture, and for that bigger picture you thought about, okay, well, this sample that we have collected comes from a bigger population, so you had a sort of sample, if I can sort of say sample, that contained, say, these, say 5 observations, say about heights or wages or education of 5 people, and you organize it in a spreadsheet, in a column or several columns in a spreadsheet, and you looked at the summary statistics or some aspects of those data you had. Now when you want to learn from it, you realize that these things come from a bigger group of population of these stick figures, like this. And then for example, this guy is just these ones chosen from this population, the other one is, say, this one chosen here, and so on. So what then we want to do, we want to use our sample to ask or answer questions or learn things about the population. So this is the population of Australia. We have a sample of observations of, say, a small group of people that we have chosen, and based on that we want to learn about population. For example, we want to learn things about what is the probability that a random person in Australia earns more than $100,000 income in a year. And we understand that with saying, okay, what we want to learn is the proportion of people in Australia who earn more than 100,000. So the probability, we understand it as population proportion. And we want to know whether we can say something, we can learn something about that proportion or estimate that proportion by looking at our sample. That's fine. It's a perfectly good way of understanding this, but it has some limitations. For example, if I ask you a big picture question of what is the probability that Reserve Bank is going to increase the base interest rates in Australia in March, or I ask you the question that what is the probability that Chinese economy is going to grow by more than 6% in 2017. Now, what are these probabilities? Can you understand them as population proportions? Can you sort of imagine a population of many, many, many infinite number of Chinese economies, and then you're going to say, well, the proportion, the probability of China's economy growing more than 6% is the proportion of those Chinas in this population of infinite number of Chinas in 2017 who grow by more than 6%. Yeah, you might be able to imagine that. It's a sort of stretch your imagination and think about that, and define that as the probability. An easier way is to assume that any uncertain object that can have several different outcomes to be a random variable, and assume that also that these outcomes are not haphazard, but they obey some rules, some probability law. So some outcomes are more likely than the others. So instead of looking at imagining a population of stick figures and thinking about, for example, the income of these stick figures in the population of Australia, if we are interested in income, we're going to assume that the income is a random variable x, which will have different possible outcomes, and these different possible outcomes will obey some probability law. And what we're going to do is, our objective is to learn about this probability law, or at least some aspects of this probability law, like the expected value of the distribution, or the variance of the distribution, and so on. So to make it concrete, I'll start by defining random variables. So it is instructive to start from discrete random variables. It's easier to understand. Discrete RVs, and that's a random variable that has a finite set of possible outcomes. So x is a finite possible outcome. Example is rolling a dice, and possible outcomes of so this x is possible outcomes called x, and there can be 1, 2, 3, 4, 5, 6, and then probability of each of these outcomes. I put it in, organize it in this table. So p, and p for xi, I is 1 to 6, and pi, probability of each of these outcomes. If it's a fair dice, it's going to be, each outcome is going to be equally likely. It's going to be 1/6, 1/6, 1/6, 1/6, 1/6, and 1/6. Okay, so these probabilities are numbers between 0 and 1, and probability of all possible outcomes add up to 1. So sum of pi, I equal to 1 to 6, is equal to 1. And one aspect of the distribution that we're interested in is the expected value. What's the expected value of the number that's going to show up when we roll the die? And the expected value for a random, discrete random variable, expected value of x, is we multiply every possible outcome by its probability and add them up. Here, 6 possible outcome, and you do that. 1 times 1, 6, plus 2 times 1, 6, plus 3 times 5, 6, plus 4 times 5, 6, 5 times 1, 6, plus 6 times 1, 6, you get 3.5. Okay, so that is the discrete random variable. A continuous random variable, in contrast, is a random variable, RV, is a random variable that can have any possible outcome on an interval, like the growth rate of the Chinese economy, say, can be anything between x growth rate of Chinese economy in 2017. Say it can be, the possible outcomes are anything between say -10, highly unlikely, to again +20, that's also highly unlikely. But then some outcomes are more likely than the other, and the probability law that gives these numbers, these possible outcomes, we show it by a probability density function. Probability density function is something, say, if I actually say this is going to be 0, 5, 10, 15, and -5. Very low probability, that's negative, but then it goes steeply high, and probability possibly, very highly probable is between, say, 5 to 10, and then steeply comes down again, and very, very small likelihood that would be 15% or more. Okay, so we show this PDF by this function. So this is f of x, and the property of this function is that the area under it is equal to 1. So the integral from minus 10 to plus 20 of f of x dx is equal to 1. And the probability of growth rate of Chinese economy being between any two numbers, say from minus 5 to 0, is given by the area. So that's the probability of x being between minus 5 to 0. The area under the curve between minus 5 to 0. And then expected value of x, similar to the discrete case, but this is continuous, can get any possible between minus 10 to 20 of x, f of x dx. So we multiply x by the f and sum it up, but in this case we integrate because it can have continuously many outcomes between minus 10 and 20. Okay, so what we want to know now, what we want to learn is about this population, the population density function or probability density function, and we use information in a sample to do so. And we do this with the aid of a model. And a model of economic growth in this example of economic growth in China. So we can have a model that is either predictive. A predictive model only allows us to predict what growth is going to be. Given the current set of economic conditions and economic policies, or it can be prescriptive. And a prescriptive model will allow us to say what policy to take, what actions to take, or policy actions to take to achieve say more than 6% growth. Okay, so as you can appreciate, prescriptive modeling is going to be a lot more difficult because it wants you to know the whole way that economy is going to work and what policies and how policies are going to interact, and we'll have a lot of political economy concerns and stuff, and it is difficult, but it's challenging, which makes it in a way interesting. So it's anything but boring. I won't say it's exciting, but it's anything but boring. So this is the way we're going to go, and we're going to look at how to make models to answer interesting questions. Now is a good time for you to go and read Appendix B of the textbook, in which the concept of random variable and distribution and all possible interesting features of a probability distribution function is also explained in a lot more detail. So I hope you find this useful, and see you in class. Goodbye now.